Now let us define tree using graphs. We have seen trees before where we define tree as a recursive definition. You have already given trees, then another tree can be built using putting a node on top of those trees and connecting them to the children. However, there is another way to define trees, and this is non-recursive definition, and we are going to see how that works. So again, let's consider a graph v comma e, and a graph is a tree if the graph is connected and has no cycles in it. That's the definition of tree. Graph is a forest if graph is a disjoint union of trees. A graph is called a rooted tree. So instead of writing v comma e, we write v comma e comma small v, which indicates the root of the tree. Okay, it's called a rooted tree. So the trees in the earlier lectures are essentially rooted trees, and those are actually equivalent definition. Let's look at an example. A graph to be a tree, it has to be only connected and there should be no cycles. For example, in this particular graph, we have a union of two trees. The first one has 4 nodes and 3 edges. Another one has 2 nodes and 1 edge. Let's look at an interesting question here. Which nodes of a tree can be the root? I mean, how is there some special requirement from the root? If you remember in your earlier definition, the root had a special place, the one which is on the top. In our definition, which node can play that role? It's surprisingly, any node can play the role of root. In the above graphs, A can be root, C can be root, D can be root, and B can be root. Any node can be root, and you can imagine the earlier definition based on the choice of the root very easily. Let's look at some mathematical statements about trees. Let me first define what is a leaf in a tree. In a node V in a graph, G is called a leaf if its degree is less than or equal to 1. Let's look at a mathematical statement about the trees. The statement says if your graph is finite and number of nodes V is greater than 1, then there exists a node V such that degree of V is 1. How do we prove that? Since the graph has no cycles and graph is finite, you can always construct a path which cannot be extended at either end. If you can always extend it, you need infinitely many nodes, or you are in a cycle. Since both of cases are disallowed, there must be a dead ends, and the dead ends is the point where you have a degree 1. So therefore, at least there are 2 nodes that will be having degree 1. Now, what is the use of this statement? Statement implies a very interesting theorem, which says if given a tree G, your number of nodes is just 1 more than number of edges. Okay, that's very interesting. So let's see how can we prove that. Let's consider a base case. When you have exactly 2 nodes in your graph, then there will be exactly 1 edge between them to make it connected, and therefore the theorem holds. Let's take an induction step, and we are considering when the number of nodes is n plus 1. So consider a leaf, because leaves always exist. So let's say consider a leaf V, and there must be exactly 1 edge connected to it, so that be V comma V prime. What will we do is we will remove the node V from this graph. So it will only remove 1 edge and 1 node from the graph. So now you have a graph G minus V, which is 1 node smaller than the graph G. Due to the induction hypothesis, G minus V must have V minus 2 edges, and therefore total number of edges in the graph G will be V minus 1, and that proves our theorem. If the graph G equals to V comma E be finite graph and number of edges is less than V minus 1, then G is not connected. That's interesting. Let's look at the proof. How do we prove it? Let's suppose there are cycles in the graph. If you remove an edge from a cycle, it does not change the connectedness of any pair of vertices. How do we prove this? Let's suppose you have a cycle in your graph, and this is the edge you're concerned with. And let's consider these two nodes. Okay, their path, their connected path goes via the edge of our concern, which we want to delete. If you delete this edge, you can always exist another path, because this or the edge of your concern is on a cycle. So therefore, removing that edge will not change the connectedness of any pair of vertices. So we continue to remove such edges until no more cycles remain. So now you do not have any more cycles, and since number of edges is less than v minus 1, the remaining graph is not a tree. I mean, we had proven that it has to be equal. So it's neither a tree nor a does not have a cycle. So that means what is left? It's not connected, and by the definition of tree. So here's an example. So in which there is a cycle. If we remove the node AB, you can easily observe that you can construct another path ACD between the nodes AD. Now we have seen the definition of tree. We can use this to define something called a spanning tree. A spanning tree of graph of G is a subgraph of G that is a tree and contains all vertices of G. Let's look at this example in which you have 4 nodes A, B, C, D, and you want to find a spanning tree of this graph. So you remove these edges CB and BD to obtain a tree which contains all the nodes of your original graph. Now we have seen an interesting definition of tree and some interesting mathematical statement about tree. Now we will move on to defining multigraph, which we had promised, and we will see how can we prove we can solve Konigsberg's problem using multigraphs.